Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1, and this lecture is entitled Basic Logic Operators and Functions. So contrary to public opinion, Mr. Spock is not the originator of logic. That distinction goes to Mr. George Boole, who in 1854 developed the mathematical proofs regarding logic. So what is logic? It is something akin to human reasoning, where input is provided to a system or a mathematical operation, and outputs are provided based upon those inputs. Okay, so in 1938, Claude Shannon is the first individual who applied George Boole's Boolean algebra to the analysis of electrical relay circuits, and that's kind of where the digital electronics age started. So the basic operations are these three gates who, taken by themselves, are very not impressive. However, in combinations and in increasing complexity, they can perform some pretty sophisticated logic functions. And when those logic functions are combined in an entire system, that entire system can perform some pretty amazing feats. Okay? So the basic scheme, and you may have already seen these things, the not, and or before. Right now, it's just a brief introduction to them. We're going to go into each one in depth. The basic scheme for most logic operators, which we're going to use, is if you could imagine a box that has inputs and it provides an output. What's really cool about this course, you don't need to know how it works inside the box. All you need to know is that the box works. Okay? So there are in or ins. There is a gate, and there is an out or outs. Okay, so let's say you got 2 ins, 1 out. Let's say you've got 4 ins and 3 outs. It gets increasingly complex if you've got 32 ins and 32 outs. So what you may see is the gate, a single line going into it, a little slash on it with a number over it. That's how many inputs it has. Okay, all it does is providing a easy way for you to read it. Okay, so we're going to deal with just some limited inputs on these gates right now. Okay, so a NOT gate. The NOT gate has what's called a distinctive shape symbol of a triangle with a bubble on it. It's got one input and one output. It's known as an inverter. And as the name invert applies, it takes the input, switches it to opposite land, and puts it on the output. Like I said, you don't need to know how it internally does that, how those transistors are worked out for this particular course. Semiconductor devices and circuits, yeah, you're going to probably have to know this. For digital electronics, all I need you to know is that if there's a 0 on the input, there's a 1 on the output. If there's a 1 on the input, there's a 0 on the output. For all intents and purposes, you can just pretend there's a little dude inside whose whole job is to look at the input. And if there's a 1 in there, he chucks a 0 over the other side. You don't need to know how it works. There is no little dude in there, by the way, so don't open him up. Okay? All I need you to know is that it inverts the output. Okay? Sometimes, so obviously triangle bubble, just because somebody wants to be a jackass, sometimes you'll see bubble triangle. I don't like that one. This is one you might see a little bit more often, the IEEE, which is a box, a little triangular flag on it. They're all inverters. This is the one I'm going to use the most of. What we're going to try to do is develop a truth table for our NOT gate or our inverter. What a truth table is all possible representations of input with its appropriate output. So what I'm going to do is I'm going to call an input signal. I'm going to call it A. You know what? I could call it blue. I could call it orange. I could call it banana. It's just a name. It's a signal. That's what it is. It's just a data signal. A can take any value as long as it's digital value. So 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. What I'm saying is a digital data stream. It doesn't matter what A is. X is the output. What is X? X is not A. How do we describe not A symbologically? With a bar over it. Okay, sometimes, let's say for example, a computer program, I can't, there's no overbar. You're going to see this in text often. A, bang. It's not A as in really loud. What's that saying is it's saying not A. Additionally, sometimes you'll see A with a little hash mark on it. One we are going to commonly use is this one right here. X is equal to not A. You may see these things in other text. Additionally, symbologically, I can define this as X is assigned the value not A, semicolon. This is your first preview to VHDL. Very high speed, integrated circuit, hardware, definition, language. Don't worry, we'll come back to this. All it is, it's a programming language that makes hardware, hooks up hardware. And what we're doing is we're assigning the signal X, the inversion of A. What's really cool about VHDL, it's kind of readable. I know that X is not A. It's a programming language. It's a high-level programming language. With that assignment operator, it's the alligator and the equals, okay? And it kind of looks like, taken together, looks like an arrow, okay? So that's VHDL. We'll go back to that. Okay, so let's go ahead and develop our truth table for our inverter. So all possible combinations of input. If A is a digital data stream, which can take the values of 0 or 1, what are all possible combinations of input? A can take the value of 0 or 1. Not that hard. What's our output? X. If A is 0, what is not A? It's a 1. If A is a 1, what is not 1? 0. It's the opposite. It's opposite land, okay? That's all the NOT gate does. Okay, let's move on to our next gate. That's what's known as the AND gate. So the AND gate has a distinctive shape symbol with a flat and a round, okay? It's got inputs on the left, and it's got an output on the right. You can also see the IEEE version of this, which is ins and an out, appropriate enough, with a little AND symbol. This is the one I'm going to use the most of, okay? So an AND gate. The easiest way to describe an AND gate is its output is high only if all inputs are high. Let me go ahead and write that down. And there's our verbal description of it. And I know you're going to have all these truth tables on you. This is what I remember. I don't remember the truth tables. That description right there is enough for me to understand how this gate works, okay? So when I take an AND gate truth table, let's say I've got 2 input AND gate, A and B, and I've got an output X. I could call it output Z. I could call inputs C and D. It doesn't matter. What does A represent? It's some random digital data stream. B could also be some random digital data stream. The only time X is high is when A and B are simultaneously high. So what I can do is I can develop a truth table for that. A, B, those are my inputs. There's my output X. So how many possible combinations can there be with 2 inputs? Well, B could be a 0, and A could be a 0. B could be a 1, and A could be a 0. B could be a 0. A could be a 1, B could be a 1, and A could be a 1, okay? See the pattern? Every other, every 2. If I was to expand this to a multiple input gate, so every other, every 2, don't you think every 4, every 8? Don't worry about that right now, we're just doing 2 input gates. What I'm doing is I'm exhausting all possible combinations of inputs. Use the verbal description, every possible combination of inputs. And output is high only if all inputs are high. A is 0, B is 0. What is our output? 0. 0 and 1, 0. They are both not 1. They're not both high. 1 and 0, 0. Finally, 1 ANDed with 1. That's a 1. That's the only time that an AND gate has a high output, if all of its inputs are high. So how do I verbally express this thing? Or how do I visually express this? A ANDed with b is equal to x. Okay? It's kind of like multiplication symbol. It's kind of like multiplication here. 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1 is 1. So kind of think multiplication. We'll come back to this, okay? How do I express and in a language like VHDL? X, my output, is assigned the value signal A and B. Close it, okay? So that is a VHDL coded expression for A and B is assigned output X. Okay, we're going to come back to the AND gate in a little bit. Let's go ahead and go on to our next one, which is namely our OR. The OR has our inputs, number of ins, it could be 2 or more, and our single out. And it's got this weird kind of scoop there and pointier representation for the distinctive shape symbol. That's the one I'm going to use the most. There's also the IEEE, which has a box, and our inputs, number of inputs, however many there are, and it's got a greater than or equal to 1 on it. This is the one I'm going to use the most. Again, think of the verbal description of these gates. An OR gate, the output is high when any input is high. Okay, so let's say I've got a 2-input AND gate. What do A and B represent? They represent incoming digital data. Let's say that's my output X also. A, B, X. Here's my ins, here's my out. What are the all possible combinations of input? 0, 1, 0, 1. So that's every other. Every 2, 0, 0, 1, 1. All possible combinations of input. So the OR gate, output is high when any input is high. Neither of them are high. 0. B is high. 1. A is high. 1. They're both high. 1. Okay? So an OR gate, output is high when any input is high. How is the OR gate expressed? X is equal to A or B. And I know you might be like, hey, what dummy, that's a plus. Well, check it out. It's kind of like addition. An OR gate is kind of like addition because 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1, hey dummy, it's 2. Yeah, we're limited to binary expression, i.e. 2 values, 1 or 0. Trust me, you'll learn about it later. The sum is 1. The carry out, which we'll learn later, is also 1. Don't worry about it right now, but it's kind of like addition. That is how I'm going to express it when I'm describing an expression. How does VHDL code that? My output X is assigned the value A or B. Close it. So those 3 gates, taken in themselves, very, very simple. However, taken in combination, they can perform some amazing logic functions. And your first and most immediate question right now should be, what are these amazing logic functions? So what I've done here is got a short list, and that's exactly what my intentions are, very similar to logic operators. Just give you a brief overview what these functions are, then we're going to try to apply those to a system example. So the first, and I've just got a list here, a comparator, your arithmetic functions, code conversion, data selection, and storage. Those are the main categories right there. We're just going to do a brief description of each one of these. So a comparator, it compares values. It compares numerical data. Is a number greater than, less than, or equal to another number? So one might see an input for number A and an input for number B, and just think about comparison. There are only 3 possibilities, one of which can only be true at a time. Either A is greater than B, A is equal to B, or A is less than B. Okay, so there are always 3 outputs to a comparator. Okay, and now A is not necessarily limited to 1 bit. It could be an 8-bit number. So I've got A7, A6, A5, A4, A3, A2, A1, A0. That's an 8-bit number. do the same thing for B. You've got an 8-bit number, you got 16 inputs. However, again, there still exists only 3 possible combinations. So say, for example, and I know we have not gone into binary just yet. Let's say A is the number, decimal number 5, and B is the decimal number 8. What's true? Well, A is less than B. So A equals B. That's false. That's false. That's true. So that's our inputs, and there are 3 outputs. That is the basic function of a comparator. It's just trying to compare 2 numbers, and again, there's only one possible true outcome, because you can never have simultaneously have A being greater than B and A being equal to B. It just doesn't make sense, okay? So that's the basic functions of a comparator. So the next one is our arithmetic functions. So your basic arithmetic functions, you can add something, you can subtract something, you can multiply something, and you can divide something. And believe it or not, trust me, it's true, you can do everything with an adder, okay? Because I'm going to show you guys a trick how to subtract using an adder, okay? What is multiplication? Well, it's kind of like addition done a number of times, okay? So I can definitely make a multiplier out of an adder. If I can perform subtraction with an adder. What is division? Division is just repeated subtraction a number of times. So basically just use the subtractor to perform division. What is the subtractor? It's an adder that I've modified to make a subtractor. What I'm getting at here is there are basic reusable parts that in and of themselves, they're very not impressive. However, when you combine them, you get this easily manufacturable, incredibly useful device that can either add, subtract, multiply, or divide. So this next one is a code converter. What is code? Think about it's something you're trying to send to a machine or receive from a machine. For example, an encoder. You got a big old keyboard. You want to write an email to your imaginary girlfriend. You press a key. An encoder takes that input of all those keys. What's it do? It spits out an ASCII code for that particular letter that you pressed. Okay, so that's an encoder. What's a decoder? Kind of the opposite. A decoder is taking that data, and let's say you press the number 7. What it's going to do is put it in a usable format. Let's say the decoder, let's just that guy, 2, 3, 4, 5, 6, whatever, it's 7 segment display. It's going to light up that one, and that one. It's taking that encoded data for 7, which is 0, 1, 1, 1, 1, 2, 3, 4 zeros in front of it for an 8-bit representation of 7, straight binary. It's not ASCII, I know that. So I'm going to go ahead and get rid of this. I take the straight binary number, we'll go into how to do this. Put it inside the decoder. It goes ahead and gives me something usable. Let me go ahead and clean this up again. The data selection function is accomplished with actually kind of one of my favorite devices. It's called a multiplexer, or a MUX for short. The other end is a demux, demultiplexer. Okay, think about the multiplexer and the demultiplexer as the postman. There are a number of people at the sender end, and they're all trying to use the same line. Think about this is parallel down into a single serial line, expanding back out into parallel. So a multiplexer and a demultiplexer are parallel to serial converters. A demultiplexer is a serial to parallel converter. So it's a really neat way of interfacing parallel and serial systems. And what there are is data selections. So there are inputs being fed into this. And here's kind of the address. And again, we're going to go into every single one of these things in greater detail. So don't worry about this so much right now, but understand the general concept of what each one of these basic logic functions are doing. So the address, I am selecting sender 0. And sender 0, here's another address right here. Let's say he wants to send some data to receiver 3. It's a kind of a switch, if you can imagine, okay? Now sender 1, because that's 0, 1, 2, 3, sender 1 wants to send something to receiver 1. That being 0, 1, 2, and 3. Okay, so you're using the same line. We're all sharing the same line. So multiplexers and demultiplexers are used for data selection. The last one is our storage function. Storage function can kind of be broken up into 2 general categories. number one being a counter, the second one being a register. So a counter you wouldn't necessarily think of as storage. However, it's key to the function of a counter to remember where you're at. Because could you imagine if you're counting 0, 1, 2, oh, where the heck was I? 0, where was I? So you got to remember where you were, okay? So a counter basically knows the state that it's at, and then it'll increment either up or down depending upon its mode, okay? Whereas a register is used to store data. This is again an application for serial and parallel. Think about 4 spaces, 4 little buckets into which I can pour a 1 or a 0. And let's say they all have zeros in there. And in comes this stream of data, MSB to LSB. I'm going to put a 1, 0, 1, 0. That is my MSB. That is my LSB. If this is the head of the truck, you think it's going to back in? No, it's going to go like that. The head comes in first, the MSB to LSB. Okay, so a serial truck is pulling into the garage. Who gets on first? A 1. Then that 1 moves over, and the 0 gets on. Then that 1 moves over, and that 1 gets on. Finally, everybody moves over, and the last least significant bit gets on, MSB to LSB in that direction. So when we go over registers, be aware of which is the MSB and LSB. I don't care how you remember these things, just remember which one's the MSB and LSB. I use the truck analogy, pulling into the garage. You can use loading a bus and signal file, whatever. Okay, so let's talk about parallel. Okay, now we've got that same digital data stream, 1, 0, 1, 0. If that's MSB to LSB, how do they get into a register in parallel? Everybody jumps on at the same time. If there was zeros in there, the zeros are pushed out and into which 1, 0, 1, 0 gets on. And again, that's MSB to LSB. And that kind of illustrates, again, the slowness of serial transmission and the relative quickness of parallel registers. And again, what are you using these things for? You're storing data. It could be storing a number. It could be storing a program. So these are the basic logic functions: the comparator, basic arithmetic, code conversion, which is divided between the encoder and a decoder, your data selection functions, which are divided between the multiplexer and demultiplexer. Finally, your storage, which is divided into counter and register functions. Okay, so let's go over just a super brief application of logic functions. Okay, so here's a brief example of how some of these basic logic functions can be applied to, let's say, a factory setting. And this factory makes nanobots, stuffs them in a bottle, ships them off to all over. Okay, I have drawn a bunch of basic logic functions on here. I do not have any of the connections made on these things. What we're going to try to do is do these things all in separate subsystems. Okay, the most complicated system can always be broken down to smaller subsystems. And understanding of those smaller subsystems will enable you to understand how the larger entire system works. Okay, so we're going to divide this into kind of 3 areas. This is the first area is this human interface. The second interface is the counting and the detection of how many are in a bottle. And finally, the third section right here is kind of how is this large factory being organized for production data. Okay, so let's go ahead and take this first one here, the human interface. Okay, so a dude at the keyboard, he presses the number, I want 50 nanobots in a jar. The act of pressing the 50 key is being fed to an encoder, which generates the ASCII representation of 50. It's encoding it. That is being stored in a register. And because that's an ASCII representation, we may need the binary representation. So it's going to convert it to the binary number 50. And it's being fed to this A number, which is our comparator. Okay, so what it's trying to try to eventually do is compare the number that are actually in a bottle with what the operator wants in the bottle. Additionally, we've got a little bit of feedback here because the operator wants to see what he entered. So coming out of register A, I entered the ASCII number 450. It's being now displayed on my computer screen. So we're using the decoder there too. Okay, the second portion of this, I'm going to go ahead and erase some of this. Actually, I'm going to use a different color highlighter. This is going to get crazy. And this is actually kind of the most complicated portion of the circuit right here is the implementation of the factory. Okay, so here we've got our nanobots. They are being fed on this constantly moving conveyor belt, or let's say there's a hopper or something like that. It's dropping them through here, and anytime one of those guys drops in, the counter increments. Okay, so what is a counter doing? It's just constantly counting up. If there was 0, 1 drops in, there's 1. Then another drops in, there's 2, 3, 4, 5, 6. It's detecting how many nanobots you've shoved inside that bottle. At some point, there is going to be that number that you've counted is going to be equal to what the operator wants. At that time, the value A equals B is asserted. It becomes true. Previously, it was false. Is 50 equal to 0? No, it's not. Is 50 equal to 1? No, it's not. Is 50 equal to 50? Yes, it is. Boom. The high happens here. There's a bit of a feedback. Now we want something to happen. Yes, very confusing. Let's put the green over here. It just goes there, okay, to that valves and control system. Shuts off the valve, kicks off the bottle, because we want that bottle's full. We want a new bottle in place. Okay, so it's making a decision based off of, hey, I've got it. I've got enough in that bottle. Okay, so not only does it stop the valve, kick off the old bottle, put on a new bottle, it is also allowing this register to be taking data from A and B, which is an adder, which, by the way, the output of register B is a running total. Okay, so this register B is not enabled all the time. The only time it's ever enabled is when it gets that A equals B thing. So this is an enable command right here. Enable. Okay, so this adder is taking that previously stored production data, and let's say it was 500, and then it's 501, 502, 503, 504, 505. All that data is kind of just sitting there. 505, 506, and then finally, when that A equals B is recognized, this enable pulse is asserted, the new running total is 550, and it repeats itself over and over again. And for the sake of completeness, because I want to use all our basic functions, that running total in the factory is being placed in parallel on a multiplexer. It's being sent in serial to some remote head office or something like that via a phone line, and then it's demultiplexed into the head offices. I don't require you, again, to really have the in-depth understanding of this right now, but realize what I just did right here is just use some basic logic functions which we've already discussed and show how they can conceptually interact for a larger system. A not and an and an or in and of themselves are not impressive. However, in combinations, you can create decoders, encoders, registers, counters, code converters, comparators, arithmetic operations, basic logic functions. Those basic logic functions in and of themselves are not that impressive. However, when they're combined in increasing complexity, we can perform an automated factory. Okay, so this kind of concludes this portion of the basic logic operators and functions. We're going to go into some fixed function integrated circuits that are commonly used, namely the and, or, and not, and we're going to discuss some basic programmable logic.